Thank you for the introduction, Peter, and it's indeed a great pleasure and honour for me to be here, invited to give these lectures. Unfortunately, I never met Marston Morse, but I did have the pleasure of meeting Mrs. Morse when I was here in the Institute in 83, 84. There's no particular sort of immediately apparent connection between what I'll be talking about and Morse's work, but I think in a sort of wider sense, he would have thought what I'll be talking about was very much in the spirit of his work and interests, probably what he would have called analysis in the large in those days. So anyway, so the general plan is these three lectures. The first two will be, if all goes to plan, talking roughly about things that are well known to people who work in this area. And then the last one will be talking about some more recent and more specialized developments, particularly ones which I've been interested in recently. So let's begin. And as is so traditional in lectures in this topic, let's begin by going back to work of Marcel Berger in 1955, the classification of Riemannian holonomy groups. I'm going to try to avoid specialized knowledge as far as possible, but we need to have a little bit. So what I hope you recall or have some idea of is that if you have a Riemannian manifold, then there's a notion of a parallel transport of tangent vectors. This is equivalent to what's called the Levi-Civita connection. So we have a Riemannian manifold, that's to say on each tangent space we have some algebraic structure, a Euclidean structure on each tangent space, and then by some well-known but sort of differential geometry, that gives us a way of transporting tangent vectors along paths in a natural way, in preserving the lengths of vectors. So in particular, you could transport a tangent vector from, we take a base point, transport a tangent vector at the base point around some loop, and it will come back with some typically different tangent vector. And if you take all such transports, or if you think of parallel transporting an orthonormal frame, comes back to some other orthonormal frame. So these things differ by an element of the orthogonal group. If you do one loop and then do another loop, then of course you compose these elements of the orthogonal group. So what you arrive at is what's called the notion of the holonomy group, a subgroup of the orthogonal group. If we think of fixing a base point and a standard frame at that base point, a subgroup of the orthogonal group given by all the ways you can move vectors around by transporting around loops. So in general, if we have a Riemannian manifold, so we fix the base point, we have a holonomy group G, which, well, here we'll strictly be talking about local holonomy groups, so we won't take some huge loop, and that means that our group will be connected. So G will be inside SON. Or said another point of view, if we start with our compact group G, then we have a representation of that on Rn, a Euclidean representation of our group G. So the question that Berger addressed and largely solved was to say which Lie groups G and representations can arise as holonomy groups from a Riemannian manifolds. So there are some rather straightforward things to say. One is that, of course, you could take products and say you always take products of different holonomy groups. So let's just sort of ignore that, assume everything's indecomposable. Another is that there is a classical topic in the theory of homogeneous spaces, the classical class of symmetric spaces, which is compatible with this notion of holonomy. So we get a certain list of these holonomy groups coming from symmetric spaces. But these are completely classified, so we think we know all about those and ignore them from this point of view, which is the non-symmetric examples. So the classification that arises, this is not completely what was found by Berger, but by Berger and some additional work of later authors, is that there are three families, which are more or less the ones you might have thought of, associated, speaking, to real numbers, complex numbers, and quaternions, and two exceptional cases. So the three families. If we just take an arbitrary sort of generic metric, then we get the full SON. Well, so SON, let's do just typical Riemannian metrics. The other thing we could, which is well known, is we could get the unitary group, thought of as acting in the obvious way with standard representation. So in our notation, this would be U n over 2. Thinking of Cn as R2n. And these are just what are called Kähler metrics. It's where you have on each tangent space, you have not just this Euclidean structure, but you also have a complex structure. You can multiply vectors by I, and that commutes with the parallel transport. That's what we're saying. So this is Kähler. So in particular, we can write down many examples of these. Then there's a variant of that, which we take SU n over 2. And these are just what are called Calabi-Yau metrics. Where there's a, if you like, the Ricci curvature vanishes, or there's a parallel holomorphic volume form, one could say. Then there are similarly the quaternionic examples. If we could take SP n over 4, this would be where we have an action of the quaternions on the tangent space, which again is compatible with the parallel transport. Or there's another, well, actually that would really be better going that way. There's a variant of that where we take SP n over 4 times SP1, because of the non-commutativity of the quaternions, we can sort of multiply on one side by quaternionic matrices, on the other side by quaternionic scalars, and those are different things. So actually it would be better to have put those the other way around, but make it more simplistic. Anyway, these are the quaternionic type things. But more crucially for us, there are the two exceptional examples. Which is the group, Lie group G2, acting with its standard 7-dimensional dimension n equals 7, or another example, dimension n8, with the group spin 7 acting by what's called its spin representation on R8. So I say Berger's list was somewhat longer. There were some other examples which later workers showed couldn't actually occur. And let's just pause before getting on to discussing in more detail these cases. Let's just pause to try to indicate why there should be this very constrained list. Of course, we have lots of compact Lie groups and lots of representations. Why don't we get all of those? Why don't we get much more stuff that could occur as holonomy groups? the reason is to understand roughly why is not too hard. The reason is to think of the curvature tensor of a Riemannian manifold. So in indices, we'd write this usual way, something like this. So this is skew symmetric in the pairs ij and kl separately, but symmetric if we interchange ij with kl. It's symmetric. So this lies inside the symmetric square of the second exterior power of Rn. Right? But there's also this also satisfies a Bianchi identity, which can be expressed by saying that if you take the product map from lambda 2 times lambda 2 to lambda 4, just the wedge product, then this lies in the kernel of that map. This is just it's called the Bianchi identity. Now, if you think of the lambda 2 of Rn, it's the skew symmetric n by n matrices, we can identify that with the Lie algebra of the orthogonal group, if you like, in a natural way. So similarly, if we have any subgroup of the orthogonal group that has some Lie algebra, and so we'll give a subspace inside our space of superior powers. So we have some G, we'll give some Lie algebra G inside lambda 2. So from the way the differential geometry works, if our Riemannian metric has holonomy group G, then the curvature tensor will lie inside a small piece of this given by the symmetric square of G inside here. So we need to look at the kernel of S2 of G mapping to lambda 4. So what you can easily see just by is that normally if you take most representation, and if you take a group, most of its representations are much bigger than the group. So this thing will normally be much bigger than this thing. So just on that grounds, it's very unlikely you're going to have any interesting kernel. So that sort of gives a rough idea of why we get this very constrained list. And to say that a bit more precisely, especially in view of the fine lunch I've just had in the Jim and Marilyn Simons dining room, let's mention the theorem of Jim Simons. This is his PhD thesis, I think, which gives a sort of more direct geometric interpretation of this list, is that more or less these groups and representations are precisely the groups which act transitively on spheres. It's not exactly true because there are a couple of other examples, but basically true. So a precise theorem would be that if you have, if we have some Euclidean representation, if we're in this setup, we have a Lie group with a Euclidean representation. We take its Lie algebra embedded in lambda 2. Then, if there exists some psi in the kernel of S2 of G goes to lambda 4, which is not G invariant, then G acts transitively on the unit sphere in V. Maybe we should also make this an irreducible representation to rule out. I'm not sure about that. So the point is that if in the symmetric space case, precisely the curvature tensor will be invariant under the holonomy group. That would more or less what characterizes it. So if you're not in that special situation, then the only way you can have something in this kernel is if the group acts transitively on spheres, and those things were classified by Montgomery and Samuelson, and more or less gives us this list. So that's, as it were, the traditional introduction to. Yes, but there was a case, in particular, there's the case of, I think it's the group spin 9, or there's another case related to F4, which sort of was only ruled out later. I don't know, maybe spin 9, I think, comes into it. Yeah. So there were maybe there are a few other cases which Berger couldn't eliminate, but. And of course, more to the point, we'll be coming to the fact that the other side of the coin is, why should there be any example? For many years, until the work of Robert Bryant in about 1980, it was not known that any of these things actually occurred. Maybe there was some more subtle obstruction to proving these things. It was not known.
What's D in the theorem, in the Simon's theorem?
Well, this is going to be the curvature tensor. So it's a purely algebraic theorem about a group and a representation. If you have something in this kernel which is not the G invariant, then the group acts transitively on the sphere. If you have a Lie group and an irreducible Euclidean representation, that's what happens. So, for time. All right. So that's, as I say, the traditional introduction to this area of special holonomy. For now, we're going to talk about, well, mostly we're going to talk about n equals 7 when we get onto it. But I would like to make, this is not traditional, but as I'll explain, there are also many reasons why the case of SU3 is an exceptional case. And although it's on this list, it behaves, we'll say, in some way, some of the constructions we can make for Calabi-Yau threefolds, which are different from what one can do in general Calabi-Yau dimensions. So this really triple of special phenomena one can study in dimensions 6, 7, and 8 will be the topic of these talks. And it sort of fits in with what one normally thinks of low-dimensional geometry and topology in dimensions 2, 3, and 4. Sort of 5 is the odd man out, but I'm sure we can get 5 into it somehow. But this is kind of special geometric phenomena that occur in sort of the middle dimensions, not very small, like 2, 3, 4, not just what you can do in arbitrary SUN, arbitrary dimensions. So the next thing to do is to explain essentially the algebra, or the basic, behind these special features in dimensions 7 and 8. And there are many ways one could go about that. We could talk about octonions. We could talk about spinors, or the many approaches we could take. Maybe to talk about the octonions would be the most, in some ways, the most vivid way to explain things. So that just like you take the cross product on R3, that becomes the part of the product, the main part of the product on the quaternions, because the cross product on R3. In the same way, there's a certain non-associative algebra structure in 8 dimensions called the octonions, where the main part of interest is a cross product on R7. A way of defining this G2 is the automorphisms of that cross product. So a way of defining what we're talking about in the case of this 7-dimensional manifold's holonomy G2 is on each tangent space we have a cross product, which is given by this same algebraic model, and it's compatible with parallel transport. But actually, technically, it'll be easier for what we want to do not to talk about octonions and cross products, but to do everything in terms of exterior algebra and differential forms. So that's going to be our next topic. What do we want to do? Maybe we want a big. An approach. Exterior. So let's begin with dimension 6. Let's take W, a real oriented vector space of 6 dimensions. And let's consider an element rho in lambda 3 of W star. Then, if we take any W, we can consider the contraction IW rho is in lambda 2 W star. So this is a skew symmetric form, and we understand those. They have a rank, and the classification is determined by a rank. So this is on a 6-dimensional vector space, but this can't have rank 6 because W is in the kernel of it. So it's got to have rank. Rank is even and less than 6. The generic thing it could be is 4. So let's say rho is. So we're going to use definite if IW rho has rank 4 for all W not equal to 0. That's the definition. So this is clearly an open set of 3 forms satisfying this condition. So then there are 3 basic facts, none of which are too hard to prove, but all, let's say, all are equivalent under GL plus of W, or the oriented general Levian transformation. So if you have one of these, if you have any 2 of these things, you can move one to the other one by an orientation preserving transformation. So in a sense, there's only one example. In that sense. And in fact, we can make a standard model is just to take rho, say rho 0, is the real part of dz1, dz2, dz3, when we take W as C3. So thought of as a real vector space. And in fact, the stabilizer of rho, let's say rho naught, is equal to SL3C. So that what that's saying is that, another way of saying this, is that if we're given one of these definite forms, that defines a complex structure on our real vector space, and also a complex volume form. This is precisely the group of transformations that preserve a complex structure and a complex volume form. And one can write, well, I think I'll leave it to the time is moving on, as always. I'll leave it an exercise for people who are interested to write down, starting from the definition, if we're given this, how to write down the complex structure on the vector space from these three. It's not a particular thing one can do. So this is some special algebraic feature of 6 dimensions. In general, if we look at the general linear transformations acting on the exterior powers, typically the exterior powers are much bigger than the general linear group, so we have no chance of having an open orbit, which is what we have here. You see, the set of these things forms an open subset, but they're all one orbit under the action of the general linear group. So that's a rare thing that kind of just looking at the numbers, you can see can only happen in a few cases. This is one of them. I should say this approach through emphasizing exterior algebra is nothing I'm saying is new, but in particular it owes a lot to there's an approach that's been emphasized by Nigel Hitchen. So let's go to dimension 7. Let's take a 7-dimensional real-oriented vector space, call it V. And now we're going to take a phi in lambda 3 V star, and we'll call this positive if, we want to take, for any vector V, we can take the contraction of phi, you get a 2 form. You can take the square of that in the exterior algebra, and then wedge that with phi. So this is in lambda 7 of V star, but we have an orientation. So although this is not, at this stage, this is not quite canonically R, it's an oriented one-dimensional vector space. So it makes sense to say this is positive for all V not equal to 0. So as this expression defines a symmetric bilinear form on V up to a scalar ambiguity, it makes sense to say that's a positive definite form. And we have the corresponding facts. They're all equivalent under GL plus V. So there's only one example, essentially. There's a standard model. Well, we're going to have two ways of writing a standard model. The standard model, say sub 1, relate phi naught is equal to rho naught, plus omega dt on V is equal to C3 times R. So here I mean that we take C3, we take the rho naught we wrote down before, the real part of dz1, dz2, dz3. We take the standard 2 form given by the symplectic structure, the standard 2 form corresponding to the metric in the usual familiar way, and we take the t as the coordinate on R, so we take omega dt, which is the 3 form. So this is a way you can verify that this thing satisfies this positivity condition, and they're all equivalent to this model. But now the stabilizer of this basic thing, if you like, we define it to be a Lie group G2, which is the exceptional, the 14-dimensional exceptional Lie group. A difference is that, see, this time the stabilizer is compact as compared to this time, but it has to be because, well, essentially because we fix this, we have associated to our phi, we have this Euclidean structure associated to phi. So let's so what I said was slightly unclear. I'm going to come back to say that again. But let's understand a bit more why. So if we just write down this formula here, we've defined a 3 form on R7, and certainly its stabilizer contains the group SU3, because that's the intersection of SL3, which preserves the rho naught, and SU3 omega. But it's not immediately obvious that anything else. So maybe that was all you had and then nothing interesting. Why is it we get there's some extra symmetry, we get this interesting Lie group coming out? So that's what we want to explain. And that can easily be seen by seeing another group inside here. So let's take another model. So the second standard model. So this will be an important thing, because actually important theme in this course. So let's take some time on that. Let's take a real vector space, dimension 4, with oriented and with a Euclidean structure. So here we make contact with the sort of low-dimensional geometry, the 4 dimensions. So remember, the special feature in 4 dimensions is that you have the notion of self-duality on 2 forms. So when we take lambda 2 of u star with lambda 2 plus, there is some lambda 2 minus, it's called the self-dual and anti-self-dual 2 forms. So to be explicit, if we take standard coordinates, so say standard coordinates y1, we're taking y1, y2, y3, t. I'll call these my standard coordinates on my 4-dimensional space U. Then I can write down a standard basis for the self-dual 2 forms. In my omega 1 is going to be dt dy1 plus dy2 dy3 omega 2 equals omega 3 equals etc. In other words, so we just permute the coordinates 1, 2, 3 cyclically to write down the formula for this. These are the 3 standard self-dual 2 forms on R4. But this is a theme that we'll see, that when you come down to a lot of this exceptional algebra, it all involves the fact that if you have 3 indices, you can permute them cyclically, just like when you define the cross product on R3 or the curl of a vector field. Okay, so that's what we're doing here. So now we're going to take V is equal to u times lambda 2 of u star. And then let's take coordinates x1, x2, x3 on here, corresponding to this standard basis. Of course, we could say it in a basis-free way, but that would probably look a bit confusing. Yes, I do. Sorry. Yeah. That's right. So I can write down phi prime 0 is going to be minus the sum of omega I dxi plus dx1, dx2, dx3. So that's so we've written down another 3 form on R7. The advantage of this one is this is obviously preserved by the action of SO4. SO4 acts on U and acts on here. And from thinking about, say, what we're doing is really an invariant construction, it will preserve this form. So this is SO4 invariant. Whereas, as we said, the symmetry that we see here is SU3, the visible symmetry. On the other hand, well, we'll leave this as another exercise, because time's moving on. If you just make a standard matching up between the coordinates, so you take Z1 is x1 plus I y1, and so on, and if I got it right, you will find that phi naught is exactly equal to phi prime naught. There are ways to get it wrong by getting the wrong signs and things, but let's hope I got it right. So what you conclude is if we define a Lie group G to be the stabilizer of this form, it both contains SU3 and SO4. And then it's easy to, well, then with those two subgroups at hand, one can understand what it is. The fact that it contains this SO4 shows that, so we conclude, so G, the stabilizer of, we define this to be the stabilizer of phi naught, acts transitively on S6, and the stabilizer of a point is SU3. In other words, SU3 comes about when we fix this one given direction in this R7, and then we get the subgroup SU3. But using the SO4s, we can move that unit vector around as we like. So this is equal to G2 over, or G over SU3. So the dimension of G, for example, is equal to 8 plus 6 is equal to 40. And you can write down the roots and everything from that. Okay, so that's our little treatment of the 7-dimensional theory of the special way. We don't have to mention octonions, but if you like, once you've got this metric and this phi, you can transpose to write it as a product. V times V goes to V, and that gives you your cross product. Yeah. So what I didn't quite say clearly is if we have one of these positive forms, then we get this conformal structure on V, what we've written down. But actually, there's a way to normalize the scale, a Euclidean structure. So Euclidean structure. Let's say G phi associated to all these things. You can, if you like, you can normalize the scale so that the norm, the square of the norm of phi computed using that metric is 7. If you to fix in standard. And that's what, if you wrote this thing out, it's got 7 monomial terms. So that's the natural convention to take. So, getting on. Yeah, so I'm not guaranteeing that the 3 sections advertised will match up with the 3 lectures, but I hope that they roughly. That's the rough plan. That's right. Yes, yes, all the good stuff. Keep it till later. Okay, so now we want to do the 8-dimensional case. So in practice, we're going to be for after a bit, we're only going to be talking about this G2 situation, or that, well, 6 and 7, not so much 8. But let's do it now. So the 8-dimensional case is different in that we don't write down a form with an open orbit. We write down a special kind of form, now this time a 4 form, that one could consider in 8 dimensions. Oh, so I just rubbed off one of the things. Oh no, I still got it out. Okay, so something I meant to say. We have this Euclidean structure, G phi, associated to the phi. So using that, we have a star operation, because we've also got an orientation fixed. So from this 4 form, we get this G phi, and we also get star phi of phi in lambda 4. In the standard way. I should say the metric, if we take this model, the metric is the standard one that we're talking about. So we can write down explicitly what this thing is. So now let's go to 8 dimensions. Let's follow a similar path. Let's write R8 is R7 times R with coordinate S in the R variable. And let's write down a 4 form, psi, in lambda 4. Psi is going to be phi ds, where phi is the 3 form on R7 we considered before, plus star phi. Well, this is the 4 form constructed purely algebraically from the 3 form, but via this, in fact, rather complicated nonlinear procedure, because it involves going through the metric defined by the 3 form. So again, this is so we can define a group. Say H is equal to the stabilizer of psi. Well, in fact, although in the end it'll intersection. Well, in the end, it doesn't matter if you put this in. Let's consider the stabilizer in SO8. So in fact, we could remove that, but you can see. So certainly this H contains G2, because that can act on the R7, preserving the phi and phi. So H contains. But again, maybe that's all it. Maybe that's all there is. So obviously something else. But we can do the same trick. That if we now go back to writing R7, we take our model with R7 as C3 times R, with coordinate t in that variable, and then we'll find that this thing is equal to rho ds plus omega dt ds plus another form rho tilde dt plus omega squared over 2. Well, something else I forgot to say. If said in the standard model, if rho is the real part of dz1, dz2, dz3, then rho tilde is the imaginary part. So as we say, if we start with a rho, that gives us a complex structure, and so we know what we mean to do this kind of multiplication by complex numbers. So if we have one definite 3 form on a 6-dimensional space. In fact, we get a whole C stars worth of them because we can multiply by complex non-zero scalars. But here we're just multiplying by I. Anyways, that's what the formula will come down to if we take these two, split off these 2 different R factors. And then this will be equal to, for some reason I get the imaginary part rather than the real part, of rho plus I rho tilde times dt plus I ds. So if I take t plus is as a complex coordinate, and so I call that Z4, then this is just the imaginary part of dz2, dz3, dz4. So seen in that way, our group also contains SU4, because obviously we can rotate SU. So I should have said that way around. SU4. So again, we've written down this sort of mysterious group, but we see that it contains 2 subgroups that we feel we understand. One is the group G2 we've studied before, and the other is the subgroup SU4. So using that, it's again easy to see that H acts transitively on the 7 sphere, and the stabilizer of a point is G2. So this thing is H over G2. So the dimension of H is equal to 7 plus 14 is 21. And in fact, it turns out that H is the Lie group spin 7 acting on R8 through its spin representation. In fact, so, but that's all we will need of this discussion of the 8-dimensional case. In particular, we see how we have this group acting transitively on the unit sphere, and it can be characterized as the terms of the stabilizer of a particular kind of 4 form. So I said one can actually remove the SO8 here because anything that fixes psi, one could reconstruct the metric from the 4 form psi in a similar way to we did in the G2 case. Okay. So that's completes our algebraic discussion. I think we've just got time to go on to the corresponding, to take the discussion forward to differential geometry. So let's go back to the beginning of the lecture. We talked about the holonomy group in terms of parallel transport around paths. But in practice, you never do that. You're not really going to work out the ODE for how you parallel. There's a more efficient way of expressing things. So let's just say that for those who know what I'm talking about. But if you don't, then you don't. You could just ignore it, and you'll still get on. So some more, say, differential geometry. So some theory. If we have a Lie group G and a representation on Rn, then if we have an n-dimensional manifold N, a principal G bundle over N, then we can form the associated vector bundle. Let's call it representation alpha, say. We can form the vector bundle P cross over alpha Rn as a vector bundle of fibre Rn over n. And we could consider a situation when we can fix we fix an isomorphism of this vector bundle with the tangent bundle. Okay. Because I'm not saying this has always happened, but supposing we can write down such an isomorphism. Now, supposing we have a connection on this G bundle, that will give us a connection on the tangent bundle, and on the tangent bundle is notion of what's called the torsion of a connection. So a particular situation is to say we have a connection, an identification like this, such that the connection, the G connection, is also torsion-free. Such a thing is called a torsion-free G structure, and there's another language for talking about exceptional holonomy. There's sort of a more efficient language. So that's, in practice, how we do things. So we have a notion of So, yeah, I'm going to finish this bit in the middle, I think. I'm going to come back to it next time. But we can get to the sort of punchline. So let's go back to our discussion of four forms on R8. We said the four form we wrote down is not form an open orbit. The orbit is a closed subset of this thing. So let's write, we'll call it the set of admissible forms. There's admissible four forms. Called. This is just this is just I guess GL plus 4, 8, the orbit of our model that we wrote down, psi naught we wrote down. So all the four forms which were equivalent to the model we wrote down. It's a certain set. So this group has got dimension 64, and the stabilizer of the standard one, we said that's given by spin 7, has got dimension 21. So the dimension of A is 64 and is 21 is 43. So there's a 43-dimensional subspace, the four forms on R8 of these admissible forms. That's what we want to focus on. So supposing now we have an 8-dimensional manifold and we have a four form, let's say psi, all right, omega 4 of m, is admissible at each point. So, I mean, an oriented manifold we should talk about. So at each point we have, we're in the situation, we look at the tangent space, we're going to be in the situation before. Of course, because this is an orbit, it doesn't matter if we act by this. Still, this makes sense. So this defines a G defines a what do I want to say? It defines a spin 7 structure on the tangent bundle of M. To say, we define a principal bundle such that the tangent bundle is associated to this as principal. Like the fibers, the principal bundle are just all the ways of taking a frame in our tangent space so that psi is given by the standard model, would be another way of saying it. The ways we can choose coordinates at a given point, so this thing looks like the standard model we wrote down. Yep. But this is really just we're not really doing much here. This is just the sort of the algebraic structures we have on the manifold. We haven't really, not really doing any differential geometry. But the crucial bit of differential geometry comes in the following dilemma. So if d psi equals 0, then this is a torsion-free spin 7 structure. Well, it's not precise at all. There is a canonical torsion-free spin structure on this bundle. So that's to say, all of this potentially complicated stuff about holonomy and bundles and goodness knows what, all ends up just being expressed in terms of differential forms, the exterior derivative, we know what it means by d of a 4 form, we're happy with that, a linear equation, and this complicated algebra of understanding the special admissible forms. And from that, that's all we need to talk about, to discuss these things. So in particular, these torsion-free spin, this defines a metric with, well, holonomy contained in, that's what spin 7, possibly not equal to spin 7. Like this could be a flat manifold, a trivial
How do you tell that you're not getting the symmetric spaces that you eliminated at the beginning of the constructions? So you said at the beginning,
Yeah.
you can realize all these symmetric spaces.
Right, so the list I wrote down is not including the symmetric spaces. The Berger list would be that list plus all the things you get from the symmetric
when you
spaces.
make something now, which is exotic, at some point you want to make sure it's not completely homogeneous.
Well, yeah, I think we could just check our list of symmetric spaces and see that this doesn't occur. There is, in fact, that spin 9 case is precisely that there is the Cayley plane, or what's called that. So there is some interaction, what you're saying, but not. I don't think it matters. Okay, well, I think that's a good place to stop. Now, this is the kind of where I wanted to get to. Perhaps I wanted to get there a bit more organised fashion, but and I wanted to say some more things to kind of round off this discussion. But this is basically the point I wanted to get to, that we have these special kind of structures that we can consider in dimensions 6, 7, 8. We can think about them in various different ways, but in particular, in terms of elementary differential geometry, in a sense of differential forms, exterior derivative, and this discussion that we've had about the special algebraic properties of differential forms in low dimensions. So we'll continue that tomorrow.